Record. Okay, so we've seen all this. We saw these, right? We saw the weeks as they occurred, calendar weeks versus number observation sequence number. Okay. So just for kicks, I ran a mixed design Anova with repeated measures. So you can look at that. If you've never ran it in R, this might be interesting. I also looked at the sample for complete data, which there's not a lot of, doing Levine's test for homogeny variance, some of those things, especially there are several in here, this class, that for part of your course project, you're going to analyze your data by a multi-level model and a repeated measures ANOVA and compare and contrast. There's several of you doing that. So here is, if you're doing repeated measures ANOVA, you're going to have to kick out all the incomplete people. So here's an example of counting how many people have incomplete data, as well as looking at the spread to see if you meet homogeny of variance assumptions, running Levine's test for the homogeny of variance. If you haven't done this in R, here's some example code. And then the sphericity assumption is looking at those correlations, which we have done before. And then here's the code for actually running an ANOVA, mixed design ANOVA. So there's the homework. So all along I've been telling you guys, Hawks is very readable. And some people were like, yeah, no. But how did you enjoy Hedeker and Gibbons? And there's some of the less technical writing. Hawks, we appreciate Hawks now. Now, I'm not saying he's always right, and there is definitely debate about a lot of these things, but he makes it a little bit more readable than a lot of the other mathematics authors. Okay. So I wanted to go to the schedule. Where's the schedule? The syllabus. Okay. So Alejandro, especially for your last comment on the discussion board. So let's look at the outline of what we've covered so far and where we're going, because we're about at the halfway point of the semester, believe it or not. Woohoo! So we started the course with R. We reviewed ordinary least squared regression. We went to 2 levels, cross-sectional, all the different issues with fitting those, longitudinal, and now we're kind of doing some randomized controlled trial intervention study information while we continue with those longitudinal studies. Starting next week, we're going to go into a review of generalized linear regression. Logistic regression is for when you have a dichotomy, when you have an outcome that's a yes or no. So Alejandro, you were asking, can we deal with a yes or no at multiple time points? And the answer is yes, by generalizing. So if you have 2 options to your outcome, that's a logistic regression. If you have like 3 or 4 options to your outcome, we can use multinomial generalization. If you have something where you're counting like the number of times someone relapses or the number of falls an elderly person has each month, or number of times someone's arrested, any time of these count outcomes, we can use Poisson or negative binomial. And I am doing a negative binomial one on an NIH grant. We're submitting this on the 5th of next month. That's looking at falls in elderly people over the course of 2 years with a sensor they wear to track. And so it's a multi-level model because it's repeated measures. So we're using a negative binomial. So we are going to review doing logistic, multinomial, Poisson, and negative binomial regression in single level regression. You should have gotten some of that in your 7610 or equivalent course, but it might have been at the end when you were burnt out, and it might have been very, very quickly covered. So we're going to take at least a week to review that before we bump it up into multi-levels. So if you see here, there's 2, after we get that review of generalizing, we kind of split the rest of the semester between this GEE and then the GLMM. So far we've done multi-level models. Those have both a marginal and a individual level built into it. We are modeling specifically both levels. So when we did the cross-sectional, we modeled the individuals and the groups simultaneously. When we're doing repeated measures, we're looking at change over time per person. So we're looking at the time level and the person level both. That's equivalent to doing these GLMMs that we're going to do in week, 11, 12, 13. But sometimes we don't have enough power to get these models to converge. And so there's kind of this intermediate kind of model called a GEE, or a generalized estimating equation, which does the marginal model only. It does the population only. And so a lot of times we are forced to not do the full generalized multi-level model, but do this generalized estimating equation approach because of power and sparsity issues. And so they're very popular. They became popular long before the GLMMs because they take less computer guts. Like the GLMMs take a lot of computing power, and computers 10, 20 years ago couldn't do them. So they become popular quicker because of that. So we're going to cover both of those types of models, cross-sectionally and longitudinally. So yes, you can do outcomes that are yes or no, or 0, 1 repeatedly over time. And we'll cover that in the GEE here and in the GLMM format, both of those. So you can have that as part of your project. It does mean that you will have to wait a little bit longer to actually do it because we won't be covering it in class probably, but definitely it would be great. It's a great option. And I've published several things on these. They're great. And your outcome can be anything that has 2 or 3 levels. And then the last week of lecture is kind of more on study design, missing data, and power analysis as they apply to multi-level modeling. So I do have some calendaring that I'm trying to work out right now. It looks like I am going to be out of the state the first week in November and not on Zoom calls, out of technology for the most part. So I'm going to try to pre-record lectures and have you guys watch that and get on at class and work on homework together. So I'll make the assignment a little bit more beefed up. I will be able to answer emails and discussion board posts in the evening, but I won't be accessible during the day. So I will definitely adjust expectations based on that. And then I have December 3rd and 10th. My daughter's on the high school swim team, and right now they have swim meets scheduled for those 2 days. They only have like 4 meets scheduled on the calendar for the whole semester, whole year, because of COVID, canceled all their invitational. Right now, it looks like they're not even gonna have region or state. It's kind of a bummer. But I am one of the head officials for the high school association swimming for our area in Utah. So I'm gonna have to be there as an official. So I'm not sure what I'm gonna do on the 3rd or the 10th. We do have a really big class for doing presentations. If anyone has any ideas you think will work, like I could get on later, we should be done by 5, but I don't want to take up your time outside of our allotted time, but we'll figure it out. Just if you have any ideas, let me know. I'm gonna be brainstorming for the 3rd and the 10th of December. Usually I'm able to do all the presentations in one day, but I usually only have 7, not 14. And it's an important part of the class. I don't want to skip it out because it's really important. You guys will get a lot out of each other's presentations. I always do. Okay, so there's our calendar. Anyone have any questions about calendaring?
No, but I just had one quick thought. What if we pre-recorded our presentations and watched them before class, and we spent class time asking each other questions or something like that?
Yeah, that's an option. And I did think of that one, Mike. How do you guys feel about pre-recording your presentations? We could have you submit them, the questions, and have everyone watch them by the 8th, and then just do a kind of a Q&A session, like a poster session almost.
That could be cool.
You know, who knows how much with COVID. COVID's not going to be over tomorrow. I think we've all determined, right? So there will probably be these changes. A lot of conferences are going to virtual. And so, you know, in keeping with trying to make this a realistic experience, we might be seeing more of this pre-recorded type of presentation. Email me your thoughts on that. Okay. Homework questions. We went over it a lot last time. We good there? Okay. Okay, I'm going to come over to the encyclopedia. And we're going to go over some examples in here of multi-level modeling with a longitudinal component. So let's make this a little bigger. Come on. What is it? Reset. Okay. There we go. That's a little better. Okay, so we did the pupil population. The nurse's stress was 3 levels. We talked centering some, although group centering we haven't hit hard enough. Variance components, variance explained. We did the autism. We looked at did we look at the autism? No? Candace is telling me no. Let's do the autism example. Candace will like this one because she studies autism, right? Okay, this is a study, and here's a source link if you want to find out more about it. This was at the University of Michigan. This is a prospective longitudinal study of 214 children. The children fell into 3 diagnostics group, and this is called BEST 2. Best test 2, because it was when they were 2 years old. It's whether they were diagnosed autism, pervasive developmental disorder, or non-spectrum children, which are not included in this. So for the purpose of this analysis, we either have autistic children or pervasive developmental disorder. Candace is laughing at me. So those are our 2 diagnostic groups, and it's based on their 2-year-old diagnosis. And then the children were followed up at ages 2, 3, 5, 9, and 13. So why so far? Can you see that we need a multi-level model here? We have repeated observations on the same kiddo. Now checking the ages, are these equally spaced or unequally spaced?
Unequally.
Unequally spaced. And that probably because they thought the kids are going to be changing more at the younger ages and more stable over long term. So that's probably why they chose these ages. So not all children were measured at all ages because, let's face it, human subject, repeated measures, you got attrition, you got a hard time getting people, you got lots of missing data. So one of the objectives of the study was to look at the influence of the initial diagnosis category, their language proficiency at age 2, and other covariates and their developmental trajectories of socialization. So that's this VSAE variable, looking at their socialization development over these ages. So this was a clinic-based sample. They were in a clinic before age 3. So the VSAE is the Vineland Socialization Age Equivalent Score. Candace, is this a real thing? Yes.
Yep.
Okay. So for your information, it's the combined score that included assessments of interpersonal, play and leisure time activities, and coping skills. So this is like a total score. So their initial language development was this SICD, the Sequenced Inventory of Communication Development. Have you heard of that one, Candace?
No, I haven't.
Okay. Well, they got them a score on their language when they were 2. We'll assume it's really good. And so based on that age 2 language development communication, they put them in one of 3 groups at age 2. So at age 2, they were either really bad at communicating, or fairly good for communication. So we have their initial diagnosis and their initial communication skills. And then we follow this Vineland socialization skill over time. So the variables in the data set are the child ID, the number to track them with, the SICD-EGP, it's their assessment of expressive language development group, which is either low, medium, or high. Age 2 is a variable where we've subtracted 2 from the age. Why would we want to subtract 2 from the age?
Because we're starting to measure at age 2?
Because we're starting to measure it at these kiddos at age 2. And so we want the intercept to be meaningful. So we center at the initial observation, which is age 2. So the variable age 2 already has the number 2 subtracted from the age so that 0 is the start of the study. So the repeated measure is this Vineland score. We also know the child's gender, race, and their best test to diagnosis. So here's our data set.
I
Lovely.
have a quick question.
Yeah.
With the best test, the sequenced test, are they getting a new score on that one on all the same times they're getting a new score on the Vineland?
This SICDE
Yeah,
GP, that high, medium, low, that's only at age 2.
just the first. Okay.
And this best test 2 was only at age 2, either PDD or autism. So those are time invariant because we're only doing them once. So yes, their socialization probably changes and their diagnosis could theoretically change if there was a mistake or something. They're probably not changing that much, right, Candace? You were saying no. But the only thing that they repeatedly measured in this data set is the Vineland. That's the only thing that they repeatedly measured. Everything else is a person-specific variable. Good questions, because it matters, right? It matters if you repeatedly measure something or you only measure it once on how it gets entered into the model.
Yeah, like we have 0 more level 1 variables at all.
Yeah. So here is the look of the data set. So this first child was male, white, had persuasive developmental disorder. Their initial socialization was high, and across those 5 observations made it. So we have OBS number goes from 1, 2, 3, 4, 5. Age goes 2, 3, 5, 9, 13. Age 2 is the age minus the number 2, so it starts at 0. And then here's the Vineland score. So this first little boy went, there's Vineland, and this is the age adjusted score, goes 6, 7, 18, 25, 27. And then let's see, the second little boy is a boy who's white, who has autism, was initially low on the communication, and their Vineland goes 6, 7, 7, 8, 14. So that's what our data set looks like. So each kid has 5 lines. So there's 1 line per observation. A group of lines makes a kid. So we have a sample of kids. On each, there's a sample of observations at purposely chosen time points. And I can pivot it to make it in wide format. Now, what's the good thing about wide format? What can we do with wide format?
Descriptives.
Descriptives, yeah.
Descriptives, correlations. What can we use long format for? I'm setting my timer so we get a break. I forgot to start it, so I just
MLM modeling.
ML modeling and plotting for the long format. So it's good to have both. Okay, so first we're going to explore this so we see it. So let's see. So autism, in our sample, we have 155 kiddos. Yep. Wait. Yeah, 155 kiddos. 155. It looks like 65%, almost 2/3 have autism. So did they randomize autism? No, I don't know how you would do that, right? They came to them either with or without autism in this clinic. The low, medium, high is their communication when they were 2, when they first saw them. And it looks like they're fairly even. There's a few more in the medium than the high. So what does this p-value over here tell us?
Well, it's either going to be the statistically significant between the levels. of low, medium, and high.
Something's going on between diagnosis and communication at age 2. They're not independent. So when the rows are a categorical variable and the columns are a categorical variable. It's doing a chi-squared test of independence. So this is telling us that the high, medium, low breakdown is different for autistics and pervasive, or autism is more or less likely depending on which of these categories. There's something, they're not independent. There's some kind of connection there. And if we look at the percentages, the low communicators have a 70, almost over a 2/3, a 3/4 chance of being autistic. In the medium category, we're only seeing 65% of them autistic. And in the high socializers, less than 50% or closer to 50%, under 50% are autistic. So the autistics are more likely to be in the lower communications. Does that make sense, Candace, with what you know about autism, since that's your focus?
Yeah.
Yeah, so that supports what we know about autism. Okay, gender. What does this say? This p-value of 0.706.
Within each of the levels, gender isn't significantly different. Like it's pretty much the same.
In low, medium, high communications, the genders about, not that males and females are the same, but the percentage of male and female remains constant across. So here overall, we have 86.5% male. In the low communicators, it's 89. In the medium, it's 85. In the high, it's 85. It's fairly consistent across those communications. And then race. Nothing going on here. So among each race, the communication breakdown, low, medium, high, is fairly constant. So this was a good demographic check. Okay. And let's see, this one, what do we do here? Oh, this is looking at, okay, let's keep going down. Wide format. Okay, here's the Vineland score. Now, when I've done this, yeah, Vineland scores. So this is all the Vineland scores, or is it? Oh, this is wide format. So this is only the Vineland at age 2. Is there a difference in the Vineland at age 2 among these communication groups? The low communicators have the lowest Vineland average. The high communicators have the highest Vineland score. And this is only at age 2. So this is like their baseline Vineland. And it makes sense that those would be associated because they're both measuring socialization, communications. There's a lot of overlap there. Okay, here we go. This is, at this point, we're going to look at missing data and attrition. Anytime you do repeated measures on the same person or longitudinal follow-up, you're going to have human attrition. Human people just can't be counted on. And even if they could, things happen, you know. So here are some packages and some tools for investigating missingness. So if you have missingness, you need to document how much missingness and the patterns of missingness. You can't ignore it. And this is something that is often not written about in journal articles. And I will tell you that you will probably have a reviewer jump on you if you don't. Now, it is kind of a crapshoot. You guys noted this in the discussion post about writing about randomization. How many times do you read an article? Does it really tell about the randomization? And the treatment of time. Yeah. Can we have our field do better at this? Absolutely, there's room for improvement. So the nice thing about R is there's some really simple functions and packages to make this not painful to do. So here I've taken my wide format of my data set and using the Vim package, the AGGR function, I gave it some options. I want to show numbers on the far right and give it counts instead of proportions, but that much code, not a lot of typing, gives us both of these figures. The figure on the left tells you how many people are missing on each variable. So how many kids are missing their child ID? None. How many are missing gender, race, and their baseline scores? None. We got everyone taken care of at baseline. But look at the Vineland. At baseline, most of the kiddos have the Vineland. But then it starts to be missing for some of them. So this tells you, this first on the left side tells you a bar plot to show you the frequency of missing for the variables one at a time. The panel on the right side shows you patterns of missingness. So the first, and it has it by frequency. So at the bottom, this is the most frequent pattern. There are 42 kids that have everything except for Vineland at age 5. It's red because it's missing. So they have child ID, they have gender, race, best to. How many kiddos have complete data for all the variables and all the 5 Vinelands?
41.
41 out of 155. Would you want to do a repeated measures ANOVA on this data set? What's going to happen to your data set? 155, 41. You're losing power. Are those 41 going to be the same or different than the 100 and whatever that are missing? Are they 41 probably representative? Who knows? That's a lot to throw out. Okay, so this can help you figure out how much missing data you have. So this is the Vim package AGGR function.
Sarah, could you show again quickly the code where you actually tell it what like variables to look at?
It'll do all the
it does all of
variables that are in your data set. If you don't want to do all of the variables, after you put the name of the data set, you'd want to put a step in here that said dplyr select and then list out the variable names you want. Because sometimes we have a data set that has 300 variables and we don't care about all of them, right?
And you would have to choose like each variable and each time point like separately in this case. Okay. Yeah.
It is because by default, it's going to look at all of the variables in the data set. Yeah. It's a pretty slick function. The second one, this is NANIAR. I don't know how to say it. It's kind of a play on Narnia. You know, what happened in Narnia in The Lion, the Witch, and the Wardrobe? The kids disappeared, right, into the wardrobe. It's kind of, and NA is the what we use in R for missing. So NA Narnia. Yeah. So if you take the name of your data set and plug it into this Missingness for visualizing missingness, each person is a line across, and gray means the data is present and black means it's missing. So you can kind of see which variable, and it has each of these variables. So that Vineland at age 2, only 0.65 are missing. But if we go over here to Vineland at age 5, 41% of our sample is missing the Vineland at age 5. And you could, so that's the viz-miss function. There's one called ggmissvar, GG for grammar of graphics, and it does it as a little line plot for number of people missing. And then you can split that by high, medium, and low to investigate is missingness more prevalent in one group or the other. I don't want to spend a lot of time on this, but there are lots of different ways to visualize your missing. This last one down here is probably my favorite. It takes the GG missing upset, and here I only want to look at the 5 Vinelands, and I want to keep them in this order. I'll let you peruse the code, but I want you to look at this figure that it makes. I've specified Vineland at age 2, 3, 5, 9, and 13 in the order they were. And then the black dots are missing. So this highest 42, this is the people that have age 2, have age 3, missed age 5, and came back at age 9 and 13. Now it doesn't have the 41 complete cases on here. It just has the people that were missing at least something. And so you can see the patterns of missingness. Right here, there are 2 people that Vineland was at age 2, missing at age 3, came back at age 5, and then missing at 9 and 13. So you can see all the different ways people could have skipped visits. Let's get a little smaller. There we go. Okay, I want to skip over some of this descriptive stuff to person profile plots or spaghetti plots. So here I have connected the dots for all the kiddos using both a flexible and a linear, which is a low S. The linear is the regression line. The flexible is the low S moving window average. And here we have all the kiddos where their points are connecting the dots. So they're, the gray lines are all wiggly. First question, is this a linear-ish relationship, or do you think we need to have a quadratic term? Now, this is using the ages in calendar years. There's wiggle.
It looks pretty linear, and if we were to make it more equal space, then it would become even more linear, right?
Well, if we compare the red and the blue lines, they're pretty close. I mean, the blue lines have a little bit of a curvature to them, but not in this group hardly at all. It's only mostly in the middle group. So this looks fairly linear to me. Now, I would want to change it to where these visits are sequenced equally spaced to observation number. What do you think about this one? Is this more linear? Now, if we equally space those visits, we get more of the blue line curving, and the red line doesn't look like it's quite as good a fit. So in this data set, would you choose to do the years in the actual calendar years, or observation number, the sequence number?
Actual years?
Actual years would probably be better for this one. I think we decided the opposite on the homework assignment. It depends. Okay. Now, second question. I paneled this by how well they communicated at age 2. That low, medium, high. Do you think that has an effect? Does the age 2 communication make a difference on the progression of Vineland? Do those red lines have the same slope or different slopes? They look slightly different, right? More steep. The higher communicators, when they're pretty good at communicating at age 2, they tend to go up pretty fast. If they're pretty poor communicators at age 2, that Vineland sees less improvement over time. The middles are in the middle. Okay, so here's some box plots, some mean plot. There's the means plots. There's age in years versus observation numbers. You can see the bend there. We want linear. Okay. So we're going to model the loaded mean structure. So we're going to make a complex model. We've seen where we start with an empty model and add in. Instead, we're going to start with a full model and try to take off. So we're going to have fixed effects for age centered at age 2 and age squared to allow for a possible quadratic bend. We're also going to take their communication group, and the way it's set up, low, medium, high. Low is going to be our reference group because it's the first level. And we're going to look at an interaction between that grouping and their age and age squared. We're going to put in both random intercepts and random slopes for age and age squared. We're going to start with a full-blown model. Woohoo! Age centered at age 2, interacting with group. Age 2 squared, interacting with group. And in our random effects, age and age squared. Whoa. Now, to get this to converge, I had to try a couple different optimizers, because when I tried it without this control statement, it failed to converge. I put in the Nelder-Mead, it still failed to converge. I put in this, it found a solution. Okay, so here are our parameter estimates. Whew, what in the world should I look at in this table? There's a lot of stuff to look at.
Might look at which effects are significant.
Which effects are significant? Now, if using this table, how do we know if a parameter is significant?
If it has stars next to it.
The stars, and those stars are representing the p-value on a what kind of test?
Walled.
A walled test. Are they completely reliable?
No.
No, but we're going to look at them. Okay. So if you have in this model, we've got lots of variables and interactions. Where should you look if there's interactions? I've got main effects and interactions. Which one should I look at first?
The interaction first.
Interactions, okay? So let's look at the highest level interaction. Are those significant? No. So this is the group variable interacting with age squared, but the group, remember, was low, medium, high. So we're only seeing medium and high compared to the reference group low. But neither one of these is significant. So not looking good. Here's age interacting with group linearly. One of them's significant, but there's probably, we could simplify this model. We probably would be thinking we might not need that quadratic term, right? So let's go ahead and do that. Here I plotted it. Plotted the model. There's the three groups. What do you think? Is there a quadratic effect? Do those lines curve? Yes, but not very much. Is there a group effect? Are the groups high, medium, and low different? They're all three different? What about low? So low is our reference group. Is median different than low?
Yes.
Yeah, medium and low, that's the blue and the orange dashed. They're pretty overlappy.
Yeah.
But this high group, it looks like it might be different. Okay. So let's drop some things out of our model. The first thing, now one thing to notice about this is a full-blown model. We think it's too far done because it's got stuff in it that might not need to be there. But what do you notice about these intercepts? They're kind of close together. What happens over time? They go up. So the first thing, now I am replicating this example was in, I think, the Histogram textbook, and I'm replicating what's in the textbook. So the first thing they did and said, it seems like everyone's starting at the same-ish spot. When they're age 2, there's not a lot of variation. So the first thing they tried to drop was the random intercepts. So yeah, let's drop that out. And you drop out the random intercepts by putting a 0 inside the parentheses. And how do you know if that helps the model fit better? Anova, likelihood ratio test. Now we've gotten rid of the random intercept. Those random intercepts were fit with REML. So when you do the Anova, you have to make sure to say refit equals false. Don't refit them. Okay, here's our p-value. What do you think? Do we need those random intercepts? Probably not. Okay, now let's drop the quadratic slope, at least in the random component. So now we're not doing a random intercept, we're only doing linear age as a random intercept. Check its fit. Wait a second. Did we need the quadratic random slope?
Yeah.
We needed it there because remember the Anova, the likelihood ratio test, tells you if the more complicated model is worth it. And this one says, yeah, you need the more complicated model. Okay, let's see about dropping quadratic time as a fixed effect.
Sorry, will you go back up to that one above? 2A, I'm just trying to see is 2A or 2B the more complex one there?
Well, let's look at in the Anova, it's hard to read that. Let's look at them. In 2A, here's 2A. I'll tell you, 2A and 2B have the same fixed effects. It's the random effect. So in 2A, it has no intercepts, but it has age and age squared.
Okay, yeah.
2B just has age, but not age squared. So which one's more complicated, 2A or 2B?
2A.
2A is more complicated.
And then they put then up above, sorry. So they put the stars in that, the Anova down lower a little, scroll down. So they're going to put the significance next to the better model. I mean, they put that next to the 2A, so it should be easy to know.
Yeah. Because 2B is less complicated. It only had 11 parameters, where 2A has 13 parameters, because it adds in age squared, variance, and then the covariance between age and age squared. Okay. So we decide 2A is better. So now we're going to try the fixed effect for quadratic time. And to do that, that's fixed effects. We need to refit 2A with ML so that we can take off that quadratic time. So 2A was our previous best model. 3 is our next model we're going to test, with removing the fixed effects for time, age squared. Interacting with group has to go with it. Okay, so which one's more complicated, 2A or 3?
2A.
2A is more complicated. Why hasn't, oh, 2.5 minutes. I'm like, why hasn't it gone off yet? Okay, so I do the Anova. Now, these models were both fit with ML, so we don't have to say the refit equals false.
Yeah,
Okay.
I don't get that.
Huh?
Because they both have random effects in those models. So
But what is it we're dropping / adding?
a fixed effect.
A fixed effects. So that's why we're using ML, because the things that we're adding and taking away are fixed effects. If you're adding or taking away random effects, that's when you want to use REML. They can all have fixed effects and random effects in them. It's not what's in them, it's about what you're adding or taking away.
And I thought in the Anova function that I know we can only use that if we have nested models, but I thought the models had to become more complicated, not less complicated.
Whichever order you put them in, it will sort them so that the more simplest model is first and then the more complicated model is second, no matter which order you type them in the syntax.
Even without a rank equals true statement somewhere?
Yes, the rank equals true is for the compare performance command, not the Anova. So what does this tell us? 2A or 3, which one's better?
2A, the more complicated one.
2A, we need that quadratic term. Now, when we looked at the plot, the curve was very slight. And we looked at the parameter estimate wall tests, they weren't significant. But the likelihood ratio is telling us we need the quadratic term in there to make the model fit better. Now, whether or not you choose to have it be in your final model is sometimes a balance between, does it fit the data better versus is it a parsimonious simplification of what the data is telling us? In this case, I would leave quadratic age in the model. So I would say 2A is my final best model. And here I've tabled it. Yeah, the wall tests are not showing up as significant, but it does fit the data better than when we leave it out. Okay, so let's see, residual diagnostics. So here is one residual diagnostic command. You're gonna have to do this on the homework, so there's a couple of them. What do these residuals look like? This first plot, does this look okay, or is it not good? Okay, good, bad.
It's got kind of a fan shape to it.
It has a little bit of a fan shape to it, but it's mostly just, it's not maybe fanning so much as this is where the bulk of the points are. What about the QQ plot? Good, so, bad. I mean, in the middle, it's perfect, right? The ends, we do have some flares on them. Yeah. The index plot, good, so, or bad. That's really good, I'd say. What about the histogram of residuals?
Sarah, what's the index plot showing again? Is that homogeneity of variance?
Yes, we're still looking for homogeneity of variance. We don't want to
Okay.
see any trends here. So the blue line, we want it to be pretty random around that lines of 0.
Okay, cool.
Here's another, I manually made a histogram of the residuals. Here I'm looking at QQ plots of these are the random effects. What do you think of these QQ plots? They're not looking so hot. Might suggest we want to look at something different. More residual plots. This is my favorite for doing residual diagnostics. So this is the one I suggest you use for the homework. And I actually typed the name of this one into your homework. I think it's like the next to last thing on the homework besides your takeaway comments. Yeah, so what do you think of this QQ plot? You like the shape of that? Is it nice and straight, Megan? You like that straightness? This is what we don't want to see from a residual plot. And here are the random effects. We do see some swing in there. Not looking so great. Here's the residuals. Really peaked. I mean, they're not like skewed or bimodal, but they're really peaked. Yeah. There is some concern. And here's the one we saw before where, is that fanning or not? This might be enough evidence for us to, I would definitely do the analysis, look at that model 3 that took out the quadratic and check its residuals and see if they're better. Deciding what's the best model depends on the likelihood ratio test and the Wald test and residual diagnostics. They're all pieces of figuring out what's the best model for your situation. Okay. So here I'm using the quick and dirty interact plot to take a look at it. So we have age is our main continuous predictor on the x-axis, and our moderator or our grouping variables that we're going to make separate lines by is that SICD group variable. What would be your takeaway message? What would you write in your conclusion?
The higher their communication abilities are when they're 2, the better adaptive skills they have as they get older.
Yeah. So if you give a kid this first measure at age 2, will that predict how well they're going to do over time? And if you give this measure at age 2, and if someone's, which group should you be concerned about, low, medium, or high? Which one needs intervention more?
Like low.
Just the low?
Well, low and medium.
Low and medium, yeah. Are low and medium that much different than each other?
No.
Over time, they have about the same trajectory. Yeah. And here I showed how you can add some more code to make it like grayscale for a publication, you know, just some extra stuff. And it's just changing the plots. Now, I want to talk about one more thing while we're here. So this plot, whichever one you're looking at, the colored, the black and white, whatever, what it's showing here are the marginal effects. So this is on average, a kiddo that tests in the high group is on average going to follow this trajectory. So this is what the fixed effects tell you, the marginal effects. On average, all kiddos like them will follow this path. The fixed effects tell you the marginal average. What do the random effects tell you? They tell you how much each individual kiddo differs from the group. So the fixed effects here, these marginal plots, tell you the group-wise on average. You can get out of the model predictions or fits for each kiddo. Getting those out are called BLUPs. A BLUP, B-L-U-P, stands for Best Linear Unbiased Predictor. So it's basically the best fitting line for each kid instead of for the group of kids like them. It's specific, in this case, for each kid. And I'm going to show you in a second, I'm going to scroll down and I'm going to have a black line for each kid. And then blue lines are going to be the fixed effects only for the group of individuals. So here's a bunch of code. It took me a while to get this. So here is each kid. This has the raw data for each, for each kid. So each kid is different. I have it paneled out by the groups. So this blue line is the group average, but within this group, the low communicators, you can see there is some variance. So the blue line is the fixed effects. That's the slope or the prediction trajectory for the group as a whole. but the variance is how much each kiddo varies. Do they vary very much at the beginning, at initial, at time 0? At their intercept, they're actually exactly identical because we took the intercept out of the model. But over time, their trajectories differ quite a bit. So is it guaranteed that a kid in the low group is going to do worse than the kid in the high group? No, but the groups on average, high does better than low. So this difference in the black lines is that idea of the variance component, how much variance there is among individuals. Let's see. So here I've done a different panel for each kiddo. So in this first panel, this is kid number 14. And their green dots are their Vineland scores. The green line is the BLUP for that, or the dashed line is the BLUP for that kiddo. The green line is the marginal group average. So this kiddo, let's see, what does green mean? Green means they were in the low group. No, medium group. Red, this reddish color is low, green is medium, blue is high. So the green is medium. So this kiddo was in the medium. See, this green line is the same as this kid's green line, is the same as this kid's green line. The green line is the average trajectory for all kiddos in the medium group. But the dotted lines are slightly different for each kiddo. Now we could run regression on each kid. But this first kid, 14, how many data points would their line be fit to? 5 data points. How do you feel about running regression with only 5 data points? Not very stable. So sometimes we talk about multi-level modeling as a 2-stage approach, or this word shrinkage. So when we make this BLUP, the best linear unbiased predictor for kid number 14, we don't just look at the 5 data points for kid 14. We also shrink or borrow information from all the other kids that are in that same group. So the multi-level model is fitting a line for each kid, but not just on that kid's data. It's also borrowing from information from kids with data that's like them. Let me point out this blue line, this kid 61 here in the middle. How many data points does kid 61 have? 2. How do you feel about fitting regression to this kid's data? Big fat no, right? But we can get a BLUP, a best linear unbiased predictor for that kid based on other kids like them. And you can't see it, the blue line is right over top the dashed line. Now look at kid 105. How their blue points are quite different than the group's average. But that's okay, we're taking them all together. This is why multi-level modeling can handle incomplete data. So some kids can only have 2 points. Kid with ID number 133, they have 3 data points. Some kids have 2, some have 3, some have 1, some have 5. It's okay because the information for any one kid is supplemented by all the other kids that are like them. Now the kid with 2 data points only provides 2 data points to the analysis. So kid number 61 only gives 2 pieces of information, but kid number 105 gives 3 pieces of information. Kid number 106 gives 4 pieces of information. So you can have people with less than complete data. It's not as powerful as people with complete data, but it's not harmful to have complete cases. Okay. My alarm went off, but it was set to silent. Well, that was not helpful. Let's have a break. Anyone want to say one last thing before we take our break, our 5-minute break? All right, we got 2 more examples to go over when we come back. Okay, I'm gonna press pause if I can get my mouse over here. Oh, I'm recording. So, okay, so we did we've done the autism. We did this chapter 5. We got a head occurring Gibbons and a randomized controlled trial example. Think we can get them both done? We're gonna try. And then remember, we're gonna go to reviewing logistic regression and such, and then we're gonna come back and do GEE and then the GLMMs. So Alejandro, there are examples down here in the GEE and the GLM that have dichotomous 2-level outcomes at repeated time points, just if you want to look ahead. So let's do head occurring Gibbons. You guys enjoyed their text so much. All right. Okay, so this is an example from chapter 4 of head occurring Gibbons. You guys had to read chapter, was it chapter 6? Something like that. Okay. So this is an analysis of a psychiatric study that came out way back in 77. So this is an older study, but we're going to use it as an example. So it's looking at the study was looking at the relationship between 2 different plasma levels for 66 depressed inpatients. But we're not going to, those 2 plasma levels were only taken in the later weeks of the study. So we're ignoring those plasma levels for this example. We're going to focus on what they repeatedly measured, which is the Hamilton Depression Inventory. So we're monitoring how depressed people are over time. And these are inpatients, so they're being treated for depression. And the covariates we have to deal with, the major one is this NDOG, E-N-D-O-G variable that denotes before the study started, when they were admitted, were they endogenous or non-endogenous type of depression? Now, I am not a psychologist at all. I don't even pretend to be one, even though I'm a faculty member for the psychology department. Weird. But we're going to just treat this as any other 2-level variable. So each person is either endogenous or non-endogenous for their type of depression. And it's only once that we determine that. So that is their static time invariant measure specific to the person. And then each person's Hamilton depression score is measured at multiple time points across time. And again, those 2 plasma drug levels, we're not even going to touch. So here's our beautiful data set. This is the data set off the Head Occurring Gibbons website. It's very much a toy data set at this point. So we have, it is real data. So here, the first person in the study, we have 6 time points, 6. Their Hamilton depression score at weeks 0, 1, 2, 3, 4, 5. And NDOG is 0. And NDOG being 0 means I think they're non-endogenous depression. So this is the data as it is available on the website in SAV SAS format. So the first thing I want to do is to clean it up and relabel that NDOG variable. So Z means they have reactive depression and 1 means they have endogenous. I want those labels so I don't have to keep going. Now, what was 0? Okay, so now I put it as the actual word in there. So now, not many variables here. This is a toy data set. In real life, would you only have this many variables? I doubt it. You'd have a lot of variables, but we'll just go with it. Okay, so here it is in wide format. So person number 1 has these 6 Hamilton depression scores. What's going on with person number 6? Their scores go 26, 22, 18, 7, 4, 3. In this scale, higher number means more depressed. Smaller number means less depressed. So person number 1 is getting better. Okay, so here's our sample size. We have 66 in our sample, roughly close to equal-ish between the reactive and the endogenous types of depression. Here's our sample size. At baseline, 61 people were observed. At week 1, 63 were observed. What in the heck happened? Two people missed their initial measurement. Lovely, isn't it? Look at week 3. How many people do we have scores for? 65. Ha! We're getting more scores as we go along. And then it dives down to 58. So I can use that Vim package or the Narnia package to check out how many people are missing. So it looks like the most common missing pattern, there are 8 people that have all but the last appointment. And then we've got a few people that are missing one at a time, and there's only one person who missed multiple weeks. At least you can talk about it now. You have a picture, you can talk about prevalence and patterns of missingness. Okay. So we really want to know what's happening to depression over time, and is it different for those 2 groups, the reactive versus the endogenous? And we can make tables, we can make plots, but we're here to model it. So here is a nice spaghetti plot. 1 line per person. What can you say in general?
Depression goes down.
Going down. Is it going down linearly or curvilinear?
Kind of looks curvilinear. I mean, there's
Can you
a
tell?
binomial.
What does this look like? This plot looks like a hairball. So what can we do? What can we do to this plot to make it more able to investigate our question?
Could fit a regression line and then the flexible line.
The
as
low
well.
S and the regression line, yeah. Also, remember, what was our question about? It was progression over time for
Well, the 2 different types?
the 2 groups. Can this picture show us the 2 groups?
No, so if we panel it or separate it somehow.
We could color the lines by their group. I did that by saying color equals NDOG. Or I like the idea of paneling it too. Now here's box plots. Ooh, okay, so here's the panel. Now that I've paneled it, is there visually anything you can pick up with your eye for these 2 groups? Are they progressing at the same way?
It kind of looks like maybe the endogenous just does start with a higher intercept.
It looks like the endogenous start slightly more depressed. What about their progress over time?
Maybe a little bit steeper. So
Okay, maybe. So the main effect of NDOG of the group variable would say they start different. A time by group interaction would say they decline different. So when we fit this model, what do we want to include? What do we want to test? What kind of term? An interaction between some time variable and this endogenous reactive group variable. Now, I did this where I put the box plots because I think it's important. If we were going to analyze this by repeated measures ANOVA, what's one of the main assumptions of ANOVA?
Homogeneity of variance.
Homogeneity of variance. Is the variance, the spread, the same at all time points for both groups?
No.
Check out the size of those boxes. Are they all the same width?
Mm-mm.
There's a lot more spread at some of these later time points and less at some of the earlier. Definitely questioning the homogeneity of variance assumption here. Here I did it as a violin plot. Just a lot of this is just descriptive. Okay, here is a means plot. These are the averages. The dots are the averages for each group at each time point. So instead of the spaghetti plot where we're going, maybe they're declining at a different rate, looking at this plot, do they start at different averages? Yeah, maybe. But do they decline at different rates? Not looking so sure right here. They look fairly parallel. So let's try it in the model. Okay, here I put the regression and the low S that Carly was talking about to compare them. Okay, here they are. Here are the 2 low S smoothers. Yeah, it looks like they're definitely apart, but maybe not different rates. Okay, so all of these are just different ways to visualize it. So I did the correlation matrix. Okay, here's the correlation matrix for everyone all together. What do you think about the sphericity assumption? Sphericity says that all pairs of time points have the same correlation. Time points that are close together have correlation in the 0.5-ish range, 6. Time points that are further apart have correlations of only 0.2 or 3. We have a decay in correlation over time. Now, there's something interesting in this example. I've looked at this a lot. Look right off the diagonal at these numbers. These are time points that are adjacent in time. So from baseline to week 1, the correlation is 0.49. From week 1 to week 2, the correlation is also 0.49. But from week 2 to 3, the correlation is really strong. What about 3 to 4? Even stronger, and then it kind of dives. I've thought about this for a lot. Why would we maybe see increasing correlation over time? Anyone have any ideas?
Well, yeah, I think it was like a learned effect, but that wouldn't apply here.
No, maybe not a learned effect. What's going to happen to these groups over time? Yeah.
Does it have to do with like the acceleration, like the rate of change in the slope over time?
It could. It also, I thought it might be attrition. What happens if you have people leaving your study? The ones left behind are usually a smaller, more uniform group. We're just kind of looking at the pattern. No matter what the reason, is the sphericity assumption violated or does it hold? Very questionable.
Violated, especially because it goes up and then down. It seems like that's
up and down, and it's not so much on one diagonal. It's like as you move further apart in time, it becomes weaker correlation. And here I did it for each group, and you separately, you see the same thing. Okay, so let's move into multi-level modeling. Okay, this time I'm going to start with the empty model. So I just have week here. I decided to use week, random intercepts only. Here we go. Here's the plot. Is there change over time? Yes. Okay, so here I have added in the blups. So there's a line for each person. Those are the person-specific lines, the blups. And then the dark blue line is the marginal average. So the fixed effects tell you the blue group line, and the dashed black lines tell you the fixed and random together for each person. So is there variance in each person intercept? Yes. Now in this model, where's the model? Way up here. Okay, I only allowed the model to have change, linear change for time, and an intercept for each person. So when I look at the plot, notice I have one slope, one fixed slope, but random intercepts. Each person gets their own intercept. On purpose, because of the way I built the line, I did not include a random intercept, so everyone looks like they have the same slope. And this is page 55 in Hedeker's book. I'm trying to replicate Hedeker's example here, so I tell you that. So we can look at ICC. Since this was a no model, we have this ICC. When we do ICC, what does ICC tell you? Let's look at the smaller one, the conditional ICC. What does 0.32 tell us?
I think it's the amount of the variance attributed to like individuals. So like in the clustering of individuals. I don't know if that's right.
Yeah, so and another way to say it is person to person variance accounts for 32-ish% of the variance in depression scores at baseline, because we have week in here. If we also look up here at the regression, where's the correlation plot that we looked up? Here's the one for everyone. The average correlation in here is about 0.32. That's what the ICC is also telling us. Okay, so there's okay. So now this 0.46, what is it telling us? that tells you the amount of variation in depression scores that's accounted for by person-to-person differences and
Time,
linear
right?
change over time.
Mhm.
Okay, and here's our R squared. So it's another way of saying that linear growth accounts for 31% of the variance in change over time. The conditional R squared tells you how much linear growth and person-to-person differences account for. So, yeah, we got weak in there. Is that all we need to look at? Is just weak? What was our research question about? Not just weak, time change, but
Group.
group. Yep. So here I did a single level model compared to the multi-level model, just because that's what Hedeker did. But before we add in group, we're going to try the random slope for week. So we know each person has their own intercept, but now we want to know, does each person have a slightly different slope? And that would be a random slope or a random effect for week. So notice my equation, I still have the fixed effect for week. There is an overall group, everybody slope, but is there also differences in slope for each ID, for each person? Now here I put them up here in the model, lovely, lovely. How can I compare these two models besides making a table? How can I assess which one's better?
Log likelihood.
The log likelihood test, the deviance difference chi-square test, and we can also use that compare performance Bayes factor comparison. So here I do a likelihood ratio test between both of them. And I said refit equals false since they're both fit. Which one fits better? Oh, it didn't even show decimals. The p-value is about 0. So which one's fits better?
The second one.
The more complicated one, which is the one that has random intercepts and slopes, not just the random intercept. Now I can do that performance compare performance with rank equals true, and it will include not just AIC, BIC, all this stuff, but also this Bayes factor and the performance score. And it tells me which one fits better. Random intercepts and slopes. Okay, so when I have random slopes in there, we still have a single fixed slope because we don't have group in there. But check out the BLEPs now. We're letting each person not just have their own intercept, but we're also letting each person have their own slope. See how those black dotted lines are all sloped slightly different? The variance component, where is the model? This variance right here, this variance is how much each person's effective week, the slope over week, is different. So this is telling us that yes, there is person-to-person differences in the slope. This one variance is telling us there's person-to-person differences in the intercept. The covariance is telling us it's negative. So when the intercept is high, the slope is low. When the intercept is low, the slope is high. So if we look at our plot, the ones that start higher on average tend to be flatter on average. The ones that start lower, yeah. Now, you can get out all these pieces in the model. I'm going to skip them because we're almost out of time, but I'm going to come down here so we can center weeks. And I'm not going to spend a lot of time on that because it doesn't change anything. So let's look at adding in endogenous. That's our group variable. Okay. So here it is. We've decided that yes, there is random intercepts for time. But now we're going to say, does the slope depend on which group you're in? Can we have a random effect for endogenous? Yes or no? Could we put endogenous here inside the parentheses? Or by week?
I'll say no.
Okay, Carly, you're shaking your head. Why do you say no?
Because group is a higher level variable.
Group applies to each person, so it doesn't make sense that it would have a different effect within a person. There's only one value for the person. Yeah, because it's a higher level variable instead of the lowest level. Okay, so here we go. We're trying to see, are there group differences in the trajectory over weeks? There, I plotted it. What do you think? Visually, is there a difference in slope for the two groups in the model? No. And Hedeker does it. So if I do the Anova, the random intercepts and slopes, the one with just weeks or the ones that has weeks interacting with group, what do we see about the p-value? Not significant. If you do the compare performance, it says week by itself, not interacting with group. Okay, last thing, and last minutes. Can I steal 2 minutes from you? Okay, you have to go, you have to go. Okay, quadratic trend. This is where we would add week squared. They're throwing in week squared. I just want to show you what it looks like. There's the bluffs. Do some people have a curved trend? Yes, but what do you notice when you look at the dark blue line? What's the curvature there? Almost none, because some are curving up and some are curving down. So as a group, it's straight. Okay. All right, you've got homework 6 going on. I'll open up a discussion board on homework 6. All of these examples we've gone over today are in the encyclopedia with all their code that you can borrow and cannibalize for your homework assignments. Use the discussion board. Email me directly if you have any questions or things with your project. The end.
What about an office hour Friday or Monday next week?
Office hour. Good question. Oh, there it's underneath here. Okay, calendar. Tomorrow, I could do an office hour at 1 or at 4 or at 5. But not all of them.
What about 4?
4? One vote for 4.
Either fine, the afternoon ones are better.
Afternoon ones are better. Megan, you have a preference?
If we could do Monday, that works better for me. But if
Monday?
not, I can just watch a.
Okay, what time on Monday?
Yeah, I mean Monday was better for me. Always in the afternoon is better.
Yeah.
Like, you were telling them like 4 or 5.
We could
usually
do
works for
both.
me.
We could do Friday at 4 and Monday at 6:30. Is that okay?
Yeah, that works for me. I don't want you to feel like you have to work at 6:30 though.
Not a problem. 2's not a problem. 10 is a problem.
Right.
Let's see, Allison, does at least one of those work for you?
Yeah, Monday's better for me too.
Okay, I know for some people, Mondays are out. Alex, does one of those work for you?
Yeah, Monday at 6:30 is good for me.
Okay, Carter?
Yeah, I could do
That's
Monday
perfect.
if Monday works for everyone, so that you don't have to have 2.
Well, I'm okay having 2. Carter?
Monday is best for me.
So there's lots of votes for Monday, so we'll definitely do Monday. I'm okay doing Friday as well, because I know of several people that have said Monday afternoons don't work for them. So I'll do both. I'll send the announcement out right now.
Thank you.
Thank you.